Here we have the Chapter 10 Assigned Homework Solutions. Question 4 says that sometimes we attempt to determine whether a person has a fever by placing a hand on his or her forehead. Is this a reliable procedure, and what assumptions do we make in this process? And the answer is no. This is not a reliable procedure. We are making assumptions because, well, first of all, measuring temperature using your hand is subjective. We perceive temperature subjectively, and a lot of it has to do with the temperature of our skin. So you assume that everybody has the same skin temperature in this procedure, and we don't. So it's not a reliable procedure for measuring temperature. Question 11 asks, if we have two cities, one near a large lake and one in a desert, and both have the same high temperature during the day, which city, if either, would we expect to cool down more rapidly once the sun has set? And here on the left we have the city in the desert, and here on the right we have the city kind of like Erie, next to a large body of water. Now we know the specific heat for sand is less than the specific heat for water, so we would expect the city near the desert to cool down more quickly. The water with the higher specific heat capacity is going to be more, is going to hold the city more temperate or more moderate. It's harder to change the temperature of the water. Question 12 asks, is it possible to add heat to a substance without changing its temperature? And it is, in the case of a phase change. If we're going from, say, ice to liquid water, then we can have ice at 0 degrees Celsius, and we can have water at 0 degrees Celsius. And we know it takes heat added in order to turn the ice into water. So we are adding heat but not changing the temperature. Question 16 says, when the liquid in a heat pack freezes, does the heat pack get colder? And explain. This is outlined in your textbook in the Everyday Phenomena box 10.1. But if we have that heat pack, it's got the little metal disc in the inside, and you click the metal disc and the substance inside, the liquid inside, freezes. But when it freezes, it's actually supercooled below its freezing point, and it emits heat energy, which is why it's a heat pack. If it got colder, it wouldn't be much of a heat pack. It would be a cold pack. Question 24 says we have an ideal gas and it is compressed without adding any heat. So we take its initial volume and we reduce its initial volume. So we have the same amount of gas, but it's compressed into a smaller volume. And it asks, will the temperature of the gas increase, decrease, or remain the same? Well, we know there are the same number of molecules and they're in a smaller area. So we know that the volume is reduced, and the ideal gas law says PV equals nRT. So if the volume goes down, then this is going to go up. So the temperature is actually going to go up. If you're not familiar with the ideal gas law, we mentioned it in class, but if you're not familiar, you can also think about it like this. By compressing the gas, you are doing work. And we know that if I do work to a fluid, I'm going to increase the internal energy of that fluid. So the internal energy goes up, and therefore the temperature is going to go up. Exercise 4 gives us the temperature on a warm summer day as 95 degrees Fahrenheit. That's pretty hot. And asks us what that temperature is in degrees Celsius, and then on the absolute Kelvin scale. So the conversion for temperature in Celsius equals 5/9 times the temperature in Fahrenheit minus 32. We put in our 95, and we get a temperature in Celsius of 35 degrees Celsius. And that actually makes sense because we know body temperature is 98.6 degrees Fahrenheit and 37 degrees Celsius. And 95 is slightly less than 98.6. 35 is slightly less than 37. So we know we're in the right ballpark with that answer. Question B asks for that in Kelvin, and we know that the conversion to Kelvin is the degrees in Celsius plus 273. I believe your book gives 273.2, but if you're close, then I'll give you credit on that one. So 35 plus 273 gives us 308 Kelvin. Exercise 6 says how much heat is required to raise the temperature of 80 grams of water from 15 degrees Celsius to 90 degrees Celsius. So Q equals mc delta T. The mass is 80 grams. Delta T, we go from 15 to 90 degrees. So we take our temperature final minus our temperature initial for our delta T. Delta T is going to be 90 minus 15, which gives us 75 degrees. And the C for water is 1. So 80 grams times 1 calorie per gram degree Celsius times 75 degrees gives us a heat added of 6,000 calories. Exercise 8. How much heat must be added to 60 grams of ice at 0 degrees Celsius to melt the ice completely? In melting, we have a change in temperature of 0 degrees because we're going from 0 degrees Celsius to 0 degrees Celsius, 0 degree ice to 0 degree water. So we can't use mc delta T. For phase change, we use m times L sub F. So Q equals the mass times the latent heat of fusion. Latent heat of fusion for water, L equals 80 calories per degree Celsius. And our mass is 60, so we have 60 grams times 80 calories per degree. And 60 times 80 is 4,800 calories. Exercise 11 we have is asking if 200 calories of heat are added to a system, how much energy has been added in joules? Well, we have a heat of 200 calories. We know that 1 calorie equals 4.186 joules. So we can just do a basic conversion. 200 calories multiplied by, we want to get to joules, so we put 4.186 joules on top, 1 calorie on the bottom. The calories divide out. 200 multiplied by 4.18 gives us 837.2 joules. And finally, exercise 13, the last one for this homework set. While a gas does 500 joules of work to its surroundings, 800 joules of heat is added to the gas. What is the change in the internal energy of the gas? So here I have a little cloud of gas, and we see that there's heat coming in, and then there's work going out. And you'll recall from the first law of thermodynamics that internal energy is equal to the heat in minus the work out. So it's a delta. If there's a change, then it's going to equal that Q minus W. In this problem, the work equals 500 joules. And the heat added equals 800 joules. So in our equation, we end up with 800 joules minus 500 joules, giving us a change in internal energy of 300 joules. And that's it.